At the end of this video, you will be able to know what is temperature, heat, and what are the effects of heat. Before differentiating temperature and heat, let's review first the concept of kinetic energy and temperature. Consider a hot case cylinder and a cold case cylinder. We know that the particles of the case are in constant random motion. We also know from that when there is motion, there is kinetic energy. So, all these case particles possess a kinetic energy due to their motion. If the motion of these particles are high, they possess a high kinetic energy, and the system in the cylinder will be hot. And if the motion of these particles are slow, then they possess low kinetic energy, and the system in the cylinder will be cold. Now, what is temperature? Well, temperature is commonly associated of a degree of hotness and coldness of a system. However, scientifically, temperature is a measure of the average kinetic energy of molecules making up a body. Remember that temperature is directly proportional to kinetic energy. Let me repeat. Temperature is directly proportional to kinetic energy. Now let me ask you, why the temperature of this hot object is high? Yes, you're right, because the particles within the cylinder possess high kinetic energy due to high motion. And we know that temperature is directly proportional to kinetic energy. High kinetic energy means high temperature. Hence, the temperature of this system is high. Similarly, the temperature of the second system is low because the particles within this cylinder possess low kinetic energy due to slow motion. Thus, low kinetic energy means low temperature. Hence, the temperature is low and it is cold. The second question is, why is hotness and coldness of any system depends on kinetic energy? Let's look at this example. During rainy season, when you rub your hands together vigorously on a cold air, the kinetic energy of your hands is converted into thermal energy due to the existence of friction between your hands. Now let me elaborate this concept further. Consider Mr. Tom and Mr. John. Mr. Tom is rubbing his hands more vigorously, while Mr. John is rubbing his hands less vigorously. Whose hand will get more hotness? Well, the answer is Mr. Tom, because the kinetic energy of his hands is high due to high motion. High kinetic energy means more friction, and more friction means more conversion of kinetic energy into thermal energy or heat energy. While in Mr. John's case, kinetic energy of his hands is smaller due to slow motion. Smaller kinetic energy means less friction, and less friction means less conversion of kinetic energy into thermal energy or heat energy. Try to do this experiment. There are lots of different scales that are used for measuring temperature. Temperature can be measured in degrees Celsius, degree Fahrenheit, and Kelvin. You might have seen how doctors and nurses measure temperature. That instrument is called the thermometer. Thermometer is a device that measures temperature. It usually applies physical properties of matter which change with temperature. What is thermal energy? Well, thermal energy is the energy possessed by an object or system due to the movement of particles or kinetic energy within the system. Consider a hot object and a cold object. We know that hot object possesses large thermal energy, and cold object possesses less thermal energy. Why do you think hot object possesses large thermal energy and cold object possesses less thermal energy? As mentioned before, hot object possess high thermal energy due to high kinetic energy of the particles. And we also know that temperature is directly proportional to kinetic energy. Thus, the temperature of this hot object is high. Similarly, with the cold object, it has a low thermal energy due to small kinetic energy. Thus, the temperature of this cold object is also low. Remember also that thermal energy depends on number of particles in a system or the mass of the system. Consider a glass of water and a bottle of water with the same temperature, 30 degrees Celsius. The water within a bottle possesses more thermal energy than the water in a glass because there are more water particles in a bottle than that in the glass. Finally, what is heat? It is actually the transfer of thermal energy from a warmer object to a cooler object. For example, consider an object with 70 degrees Celsius and an object with 30 degrees Celsius. Thermal energy will transfer from this warm object to cooler object until they both get the same temperature. And this state is called thermal equilibrium. Let's have a quick review. In the English language, the common terms of thermal energy, heat, and temperature are often used interchangeably. Although they are closely related terms, they each have different meanings and are measured in different units. What are those differences again? Thermal energy is the total amount of kinetic energy of the molecules in a system or an area, and therefore, it is impacted by size and mass. The unit for thermal energy is joule. Temperature, on the other hand, is measured in degrees Fahrenheit, degrees Celsius, or Kelvin. Temperature is the average kinetic energy of a substance or a system. Since it is the average kinetic energy, it is not impacted by the size and mass. Heat energy is the measurement of energy in transit between a system with higher kinetic energy and one of lower kinetic energy. As a unit of energy, the base unit for heat is the joule. Remember, heat energy always moves from the system with the higher kinetic energy to the one with the lower kinetic energy. Example, if I were to pour a cup of coffee over the ice cube, the same transfer of energy would occur with the faster molecules of the coffee, transferring their energy to the slower moving molecules in the ice cube. As the molecules in the ice cube speeds up with their newfound energy, the molecules in the coffee will slow down as the energy is transferred to the ice cubes. At some point, the speeding molecules of the ice and the slowing molecules of the coffee will reach equilibrium, and the transfer of energy will stop. The effects of heat are temperature change, phase change, and thermal expansion. You might have noticed that if you are trying to boil a lot of water, it takes longer than if you only wish to boil a small amount of water. This is all because of something called heat capacity. So what is heat capacity? The heat capacity of a substance is defined as the amount of heat required to raise the temperature of a material by 1 degree Celsius. However, what's more useful for us to think about is the specific heat capacity of a substance. This is, as it says in the name, a little bit more specific. It is the amount of heat required to raise 1 kilogram of a material by 1 degree Celsius. Different materials have different known specific heat capacities. For example, water requires 4,200 joules of energy to warm 1 kilo of it by 1 degree Celsius, whereas 1 kilo of mercury can be heated by 1 degree Celsius with only 139 joules of energy. We call these numbers a specific heat capacity, which is the amount of energy needed to raise the temperature of 1 kilo of a substance by 1 degree Celsius. It can also be thought of as the amount of energy released as that substance cools. So each time a kilo of water cools by 1 degree Celsius, it will give out 4,200 joules of energy to the surroundings. Remember, a positive heat energy means heat is absorbed, and a negative heat energy means heat is given off. Another example. If you keep a steel plate and a wooden plate in a sunlight, you will notice that the steel plate's temperature will rise very fast, whereas wooden plate temperature will rise slowly. This happens because heat capacity of a wooden plate is more compared to a steel plate. Remember, a material with high specific heat requires a great amount of heat to change its temperature, and a material with low specific heat requires less heat to change its temperature. And remember, two objects made of the same material have the same specific heat but may have different heat capacities depending on their masses. For example, 1 kilogram of wood has different heat capacity than 10 kilogram of wood, but both have same specific heat capacity. Specific heat capacity varies only from matter to matter. When a substance changes its state, heat energy is involved. The energy is not to heat up substance, but to separate the molecules from each other. This is known as specific latent heat. Specific latent heat should not be confused with specific heat capacity. Specific latent heat is defined as the amount of heat required to change 1 kilogram of a substance from one physical state to another without any change in temperature. So specific latent heat is the heat energy absorbed or given out when a substance undergoes a state change. For example, the heat energy is absorbed when a candle burns and a solid wax melts. There are two key things to remember. First is specific latent heat is particular to state changes. So the specific latent heat to change ice to water is different to change water to water vapor. Second is that there is no change in temperature during the change of state. It remains constant. The temperature will only change once the state change has completed. As I said before, the heat energy is not used to heat up the substance, hence no change in temperature, but instead used to make or break the bonds that holds the molecules together. There are two types of latent heat. These are latent heat of fusion and latent heat of vaporization. Let's take a look with this example. When we place a thermometer in the vessel containing ice and gradually heat the vessel over the flame, temperature of the ice vessel remains constant at 0 degrees Celsius until all ice has melted. Despite of supplying heat to ice, its temperature remains constant. This fixed temperature at which the solid ice cubes melts to liquid water is called melting point. The quantity of heat required to convert 1 kilogram or gram of solid substance into 1 kilogram or gram of liquid without changing its temperature is called latent heat of fusion. The temperature starts rising after the ice in the vessel is all melted to water. The rising of temperature stops again at 100 degrees Celsius, then water starts boiling. As water boils, the temperature level remains the same. This fix of temperature at which liquid boils and changes into steam is called boiling point. The quantity of heat required to change 1 kilogram or gram of a liquid substance into 1 kilogram or gram of gas without changing its temperature is called latent heat of vaporization. Remember that it may take a different amount of heat energy to change a solid into a liquid than to change a liquid into a gas. For example, it takes 7 times more energy to turn liquid water into gaseous water than it does to melt ice into liquid water. In short, latent heat of fusion is always smaller than the latent heat of vaporization. The third effect of heat is thermal expansion. To understand this, let's watch the simplified video from the channel It's Sometime.
Hey, did you notice that the level of mercury in the thermometer rose when it was placed in hot water? You must be wondering why this happened, right? It happened because of thermal expansion. Thermal expansion is the tendency of matter to expand on heating. This tendency of expansion can be observed in solids, liquids, as well as gases. Now, let us see how this concept of thermal expansion applies to a thermometer. A thermometer usually consists of a narrow tube with a small bulb at its one end. The bulb and a part of the narrow tube is filled with mercury, which is liquid at room temperature. Now, when a thermometer is placed in hot water, mercury inside it expands due to thermal expansion, and as a result, its level rises.
Huh?
You must be thinking how the gasoline came out of the tank, even though it was exactly filled till the brim. Am I right? Gasoline also expands on heating. So, what happened is that when the tank was filled till the brim, there was no space left in it. Now, when the bike was kept in the sun, the tank became hot, which eventually heated the gasoline filled in it. As a result, the gasoline expanded. But since there was no space left in the tank, expansion forced gasoline to come out of the tank.
Hey! Oh yeah!
Do you think that the rails bent because of thermal expansion? If yes, then you are absolutely correct. A railway track is made up of a number of rails joined to each other. These rails are usually made up of steel. Steel expands on heating and contracts on cooling. When the rails are joined to one another without leaving any space for expansion, the rails bend due to thermal expansion and the train goes off the railway track. To avoid this, the rails are not joined together firmly. Instead, each rail is connected to the other in such a way that a small gap is left in between them. These small gaps provide space for easy expansion of the rails, which happens during summer, as well as due to continuous friction between the train wheels and the rails. Hence, these small gaps prevent the rails from bending, preventing any kind of accidents.